Hi everyone. This is going to be the intro video for the optics module, and we're going to start by thinking about electromagnetic waves or light and its properties. Before we delve into the details of electric and magnetic fields, let's go back to our previous module for a second where we talked about simple harmonic motion. So if you remember, a traveling simple harmonic wave looked something like this: y equals y0 sine of kx minus omega t. And here y0 was the amplitude, k was the wave number, omega was the angular frequency, and they all sort of told us, all of this information told us how the simple harmonic motion was oscillating. So for instance, the k told us k was 2 pi over lambda, where lambda is the wavelength, right? Lambda is the wavelength. Omega is the angular frequency, but omega over 2 pi is equal to f, where f is the frequency of the wave, right? And two of these together actually told us that v is equal to f times lambda. So speed of the wave is equal to frequency times wavelength, right? So that was true in the case of traveling simple harmonic motion. And in this particular example where there is a negative sign in the middle over there, this was a traveling wave traveling to, to the right. So that was the idea. There's a fundamental sort of difference between electromagnetic fields and what we have been talking about. But before I get into that, let's once again think about what was oscillating in our first simple harmonic motion module. And we talked about several examples. There was the example of strings, there was the example of sound. And if we think about sound, what's going on is there is error between, let's say, where I'm speaking and where you're listening. If we were standing face to face, and so that air, there are pressure waves that are being created in that air, which means that air molecules, they are oscillating, right? And the particular example of sound in air is an example of what is called a longitudinal wave, right? And it's longitudinal wave because if you think about air molecules that are next to each other, they are oscillating in this fashion along the direction in which the sound is moving. So if sound is moving along that direction, right, then the air molecules are fluctuating like this. And as they fluctuate, they're hitting each other and they're probably transferring that the energy that the sound wave represents and is getting carried from one place, place one to place two, right? That's the idea for longitudinal waves. Now there's another kind of waves which we talked about, which are called transverse waves. And one example for these transverse waves was strings, right? So if you think about strings, if you have a string that is connected or fixed at two ends, then it can only oscillate like this. These are the kind of standing wave patterns that can form. But if there are traveling waves, they're going to travel either this way or that way. But if you think about the material in the string material is oscillating in this way while the wave is going perpendicular to it. And so this is an example of transverse waves. All right, so this is all about waves when there is a medium. But if you think about light, light is reaching our eyes, say from the stars or the sun, right? And we clearly know that there is no medium between stars or the sun and us. Well, there is some. There is the air close to the Earth. But if you go outside the Earth's atmosphere, there's absolutely nothing. So there's vacuum. So then the question arises, what is propagating for electromagnetic fields? And it turns out that there are these quantities called electric and magnetic fields. We will get into these electric and magnetic fields probably in the next module. But you can think of them as just these fictitious objects that exist everywhere, sort of. So for example, if you put a charged particle, like for instance an electron in an electric field, it's going to move, it's going to feel a force, right? So that's an electric field, and it turns out that light rays are nothing but perpendicular fluctuations of electric and magnetic fields. So in this picture over here, if you look at this picture, there is a light wave that is moving from left to right. Yeah, that's so the direction of this wave velocity is shown in this part over here. And what's going on is these pink arrows represent a sinusoidal oscillation of an electric field, and the blue um, arrows show the sinusoidal oscillations of a magnetic field. And in this particular case, the electric and magnetic field are perpendicular to each other, and generally, it's true for light waves that they are made out of electric and magnetic fields. Electric is E and B is magnetic field. Usually this is the convention for writing electric and magnetic fields, right? So these E and B fields are both perpendicular to each other, and not just that, the propagation direction, the direction of the wave velocity is perpendicular to both E and B fields. Okay, so if I write V vector, which is the propagation direction, then these are all perpendicular to each other. So these are all perpendicular to each other. Okay, so since the stuff that is fluctuating, electric and magnetic fields, they're perpendicular to the direction of the velocity, what kind of wave would this be? Clearly this has to be a transverse wave. So electric and magnetic oscillations perpendicular to the direction of motion of light makes light a transverse wave. So these are transverse electromagnetic or E&M waves. Okay, so apart from this, most of the other stuff that we had discussed before carries over. So the only difference being that there is no medium necessary for carrying electric and magnetic fields. Other than that, we can still write the electric field, the oscillating electric field, if it's propagating in a particular direction, we can write it at E0 vector. This will be the amplitude of the SHM times sine of, let's say, kx minus omega t, where it's moving in the positive x direction as time goes on. Right? So this is an example of an electric field. The B field could be written as, again, a B0 sine of kx minus omega t. Generally, these two will be in phase, so they will not have a phase difference. So if you look at the two waves, they're perpendicular to each other, and that perpendicular nature is given by either the B0 or the E0, the amplitude vectors. But sine kx minus omega t is the oscillation part. It's the traveling wave part of this electric or magnetic field, and that's in phase. So the E field is 0, B field is also 0 kind of idea, right? Now, this is in this particular picture, the E and the B field, oscillating E and B fields, or the light wave is traveling in the positive x direction, and that's denoted by this traveling wave, right? Whenever we have the negative sign, so that negative sign over here tells us traveling in plus x direction. And we can go further. We can actually look at this picture and see that the magnetic field is along the positive z direction. So we can write this B0 vector is just equal to some magnitude B0 times z hat. And the E0, if you look at it, it's along the positive y direction. So E0 is equal to E0 y hat. Okay. And if you wanted to write the velocity vector for the electromagnetic wave, it turns out v is equal to the magnitude of v is always the speed of light. So we'll call that c in at least in vacuum or in air, the speed of light is equal to c, and then the direction is x hat, where c is equal to 3 times 10 to the 8 meter per second. And everything else carries over as well. So for instance, k for EM waves is also equal to 2 pi over lambda EM waves. What is lambda? Lambda is the wavelength, right? And omega for the EM waves is also equal to 2 pi times f of EM waves, and often this f of EM waves is written as nu. So nu is a new thing that we just learned, nu, the Greek letter nu. So omega EM is equal to 2 pi nu. And I'm not going to write the index EM because generally F is used for sound and other waves that are propagating in media, and nu is used for light. And this is interchangeable. You can either use F or nu. It doesn't really matter. It's your choice. But the relationship that c is equal to, the speed is equal to wavelength times frequency still holds, right? Okay, so now this holds. You can ask, what is the medium here? The medium has to be air or vacuum, because if you think about it, light, when it's traveling in vacuum or air, it's going at 3 times 10 to the 8 meter per second. But as soon as it gets into a different medium, let's say it gets into glass or air, not air, for air it's the same as vacuum, but if it from air, if it gets into either glass or water, then light probably slows down. And so when light slows down, we're going to use a different notation. So we're going to say V medium for light, right? That's the speed of light in a medium. So V medium will then be equal to lambda medium, wavelength in medium, multiplied by nu. It turns out the frequency of light is tied to the color of light that we see. So we are not going to change, the frequency does not change as you go into a different medium, but the wavelength of light changes. And so this is the relationship. So as we said, in air or in vacuum, light satisfies this relationship C equals nu times lambda, right? Where nu is the frequency, lambda is the wavelength of light. And in vacuum or in air, this quantity C that is fixed is 3 times 10 to the 8 meter per second. And then you can think of how nu and lambda could change, and how one change of one could lead to the change in other, because they're tied to each other through this relationship here. So because C is constant, as you increase nu, lambda would decrease, right? Because the product has to stay the same. And so as we go lower and lower in frequencies in this chart, if you look at table 30.1 from the book, if you look at this chart over here, as we go lower and lower in frequencies, the wavelength on the other side is going higher and higher, right? And it turns out that light, the light that we see with our eyes, the visible part of the light, is just a tiny fraction of the entire spectrum of electromagnetic waves that we can access. And the frequency can go all the way from like very small. If the frequency is 0, that's not really an oscillating thing, but let's say that it starts from 10 and goes to 10 to the 23. That's the frequency in hertz, and on the other side, the wavelength, lambda, that can go then from 10 to the 7 meters all the way down to 10 to the minus 14 meters, right? And these are different kinds of electromagnetic waves. We can start at very long radio waves and then go down to microwaves, infrared. Infrared is also not visible to our eyes. It's wavelength that is longer than red light. And then there's the very familiar visible spectrum with violet, indigo, blue, green, yellow, orange, and red, right? And as you go from violet to the red side of the spectrum, the wavelength increases and the frequency decreases, right? That's the idea. And then if we go to smaller and smaller wavelengths, we have ultraviolet, and then we have X-rays and gamma rays. The gamma rays are really small wavelength light rays, right? So that's the idea. Okay, so we're going to slowly start to talk about what happens to light when it encounters, going from one medium, it encounters a different medium. So for instance, let's say a ray of light is coming from air, and it hits the surface of a window. So an air glass surface interface, what happens, right? So we have kind of already seen a little bit of what happens. Remember, C is equal to nu lambda, and this is in vacuum. Okay, so this is in vacuum, But what happens if I write this in a particular medium, let's say in glass? So V medium then is equal to nu times lambda medium. All right. And this is in medium that is not vacuum, right? I mean, it's true in vacuum as well. It's just that vacuum, in vacuum, you have to replace this V medium by C and lambda medium by lambda, right? Okay. So what is our expectation? What would happen if it hits a different medium? Well, so let's say that this is the interface. This is air, right? This is glass. And then a ray of light comes in like this. What could happen? Well, in our ordinary life, what we see is two kinds of phenomena. One kind of phenomenon is called reflection. So a part of this ray of light bounces back, right? From this point, bounces back, and another part of this ray of light goes through and gets transmitted, right? So this first part is called reflection, right? So reflection is when ray of light goes from one medium, hits a second medium, and then does not go into the second medium, but gets reflected into the first medium. So this part is going to be reflection. And the second part here is going to be refraction. Refraction is the part where part of the ray of light actually gets into the second medium. Now, in order to talk about these in a little more detail, we have to think about what are we observing, right? So that's kind of an important thing when we observe light. What do we see? So as I told you, there are electric and magnetic fields. There's this E equals E0 sine of kx minus omega t. But what our eyes can really perceive is the intensity of light waves. And intensity, remember, even for sound, intensity was proportional to the amplitude squared. So similarly here also, the intensity of the light wave is actually proportional, for light, intensity is proportional to the electric field squared. Same way with the magnetic field, but electric and magnetic field are related to each other, so we're going to just talk about the electric field, and the proportionality will give us all relationships that we need just from the magnitude squared of the electric field, right? So remember, light intensity or any intensity is proportional to the amplitude squared. So we really need to know how this electric field, magnitude of the electric field square is behaving to know what we are seeing, okay? In general, when a ray of light is incident at an interface like this, only part of it gets reflected and only part of it gets refracted. There is also a third part which may get absorbed, okay? But in this particular case, we are only going to talk about the first two cases, reflection and refraction. So part of it gets reflected, part of it gets refracted. That's the idea, right? Okay, so what else happens? Now, in the first, if you think about speed of light, right? If this was air, the incoming ray of light was satisfying this first equation here. What about the outgoing ray of light? Well, the outgoing ray of light is still in air, so it's still going to satisfy that C equals nu lambda. Okay? But that's no longer the case when you think about the ray of light that got refracted, that went into the glass, because that is in a different medium. And if the speed of light in glass is different from the speed of light in air, then it'll satisfy a different relationship, the second one over here, right? And now if you think about it, really, when light encounters a different medium, which is actually optically denser, but it can also be just denser than the first medium, light slows down, right? So if light is incident from air to glass and it gets into glass, inside glass, light feels more hindrance to its motion than it would in air, and so light slows down. So V medium, or in this particular case, V glass, is less than C, which is the speed of light in air. Okay, so lambda glass is also going to be less than lambda. And how do we see that? Well, let's look at these two relationships. As we go from the first to the second, the left-hand side, that decreases because C is larger than V medium. Nu, on the other hand, the frequency of light, that's fixed, so lambda must be also larger than lambda medium. So lambda, as light goes into a different medium than air or vacuum, its wavelength decreases, its speed decreases. Okay, so there's a way of measuring this decrease in speed, and that's known as the refractive index of a medium. Refractive index of medium. And so refractive index is defined as, we'll use the letter n for refractive index. N is equal to c, the speed of light in vacuum, divided by the speed of light in the medium. Okay, so we can call it v medium. Okay, so you can then talk about the refractive index of air. So n air is clearly equal to c divided by v medium, v air, but v air is also equal to c, so this is c over c equals 1. Okay, so the refractive index of air is 1. Okay, the other examples of refractive indices are in glass. So glass, it depends on the kind of material that glass is, but roughly it's about 1.5. It can be slightly larger. It can go to about 1.7 ish. But we'll take 1.5 for an answer for this one. And in water, refractive index of water, that turns out that that's equal to 4/3 or 1.33. So so what does this tell you? Well, it tells you that the speed of light in water is about 3/4 the speed of light in air, right? Because if we have v water, that is equal to 3/4 c, right? If we use this, then we get c over v water is equal to 4/3, which is n water. And that's the idea. Right, so clearly there are two things that are sort of different for reflection and refraction. Reflection, the first thing that is different is that because it's the same medium, the speed of light stays the same, right? After reflection, the speed of light stays the same. And the second thing that is different between reflection and refraction is that the wavelength of light also stays the same for reflection. But now if you think about refraction, both the speed of light and the wavelength of light both change. The thing that is common that does not change upon reflection or refraction is the frequency of light. That's kind of important. Frequency of light does not change. Okay, so now because of these changes, we can now talk about some laws with which if we encounter any problem with reflection or refraction, we can figure out answers to those problems by using some laws of reflection and refraction. So we'll start with the laws of reflection. And so when can reflection happen? Well, anytime a ray of light is incident on a surface. So let's say this surface is a mirror, right? So you know that mirrors reflect light, right? So if a ray of light is incident like this at the surface of a mirror, and we can always draw a perpendicular to that surface, and we will call that perpendicular to that surface a normal. So that will be the normal line, and normal is always perpendicular to the surface. Then the refracted ray of light looks like that. And then we can draw an angle like this. We'll call this the angle of incidence, the angle between the incident ray and the normal. And then we can also draw a different angle, the angle between the normal and the reflected ray. We'll call that theta reflected. Okay, so it turns out that there are two laws of reflection. The first law of reflection says that the incident normal and reflected rays lie on the same plane. And often this plane will be referred to as the plane of incidence. Okay, because the plane of incidence and the plane of reflection are exactly the same. As the law of reflection tells us, incident, normal, and reflected rays lie on the same plane. So we can just call that the plane of incidence. Okay, so that's the first law of reflection. And the second law, and this is the more commonly used law, is that the angle of incidence, theta I, is equal to the angle of reflection. Okay, Okay, now let's talk about the laws of refraction. Laws of refraction. So when can refraction happen? Well, when ray of light is incident from one medium to another. So let's say we have air and glass, right? And this is the interface between the two media. We can always draw a line that is perpendicular to the to that interface, and we will always call that line, no matter whether it's reflection or refraction, we'll call it normal. And let's say a ray of light is incident right at this point where we drew the normal, right? So it's incident straight like that. Then after refraction, this ray of light is now going to bend. Okay, that's the process called refraction. So let's first try to understand why the ray of light is going to bend. Okay, so you can think of rays of light as if they're coming together with other rays of light, right? So it's not just one single ray of light that is incident at this spot, but it's really many rays of light. But let's consider two extreme ends of a beam of light. Okay, so now when you have a beam of light like this, perpendicular to that beam, that's the place where the two rays of light are as if they're connected to each other because they are related to each other by a phase relationship. And that phase is essentially the sine kx minus omega t. And you can think of the same x and same t will give you the same phase. So essentially anything that has the same x and same t, so sort of along that, along the x and t are measured along the direction of motion. So essentially this perpendicular line, that the line perpendicular to the beam, tells you that x and t are the same, so these are phase related, right? So now you can see that one of these two rays of light is actually hitting the surface before the other one. So this one, for instance, hits the surface over here, and so at this time that the phase correlated part of the other side of that beam is still moving in air. So this was my air, this was my glass, right? Now, as soon as this hits the glass, when it starts moving inside glass, so the refracted part, it's gonna start moving in such a way that this other, beam still does not know that there's glass in front of it, right? So this beam still keeps going with the same speed while the speed of this beam has changed. So because of that, you can now think that this is going much slower, but this is going faster. In order for that to happen, this has to bend, right? So if it bends, now it gives it enough time for it to reach to the second ray to reach the surface before it also starts bending. And so now these are the coherent sort of levels for the beam that is propagating, right? So that's the idea. It's that the slowing down of light is what makes light bend when it goes from one medium to another. And so now we talked about air and glass, where speed of light is larger in air and smaller in glass. You can think of the exact same thing happening in the opposite direction. That is, ray of light is incident from glass, so in this direction. And now where will it go in air? Well, if you just reverse this argument that I gave you before, it's also going to bend, okay? Bend like that. And if the ray of light initially was coming from a rarer or less dense medium, rarer medium, and went to a denser medium, then the ray of light will bend toward the normal. If it's going from the denser to the rarer medium, it's going to bend away from the normal. That's the idea, right? So let's just write them in words. So if ray of light is incident from rarer to denser, okay, so then light will slow down. And when light slows down, ray bends toward normal, okay? And in the opposite case, when the ray of light is going from denser to rarer medium, light speeds up, and so the ray bends away from the normal. Okay, so these are sort of the main ideas for how to go about understanding refraction. But still, we have to talk about a couple of laws of refraction. So these are not really exactly the laws, but these follow from the laws of refraction. Oh, one other thing that I should mention here is that what do I mean when I talk about a denser medium or a rarer medium? Whenever an index of refraction is larger, it's a denser medium. So for instance, n air is equal to 1. So that is a rare medium. So that's generally going to be rarer medium in all our examples. And then n glass, that is equal to 1.5. So that is a denser medium. Okay, so rarer or denser is determined by how large the refractive index is. Whenever a medium has a larger refractive index than another medium, then that first medium is supposed to be denser than the second medium, right? That's the idea. Okay, so now let's state the laws of refraction. Again, the first of these laws is the same as the law of reflection. So incident, normal, and refracted rays lie on the same plane, which is the plane of incidence. So refracted plus incident and normal, right? Incident and normal were always in the same plane, right? Lie on the same plane. And what is this plane called? This plane is again going to be called the incidence, plane of incidence, right? And then there is a second law of refraction, and this law has a name to it. It's often referred to as Snell's law. And Snell's law says that if light is incident from, let's say, medium 1 and it's going into medium 2, so then we can write n1 sine of theta 1 is equal to n2 sine of theta 2, where n1 and n2 are the respective refractive indices, and theta 1 and theta 2 are the respective angles in the particular media. So if this is my picture, this is my medium 1, medium 2. So medium 1 has refractive index n1, medium 2 has refractive index n2. A ray of light that is incident like that, if this is the angle theta 1 and that's the angle theta 2, right? Then n1 sine theta 1 is equal to n2 sine theta 2. Okay, and rays of light are perfectly reversible in all of these situations. So if a ray of light is incident like this, it's going to go backward in the same fashion and it came in the first place. So again, you can see that n2 sine theta 2 will be equal to n1 sine theta 1. So this law is kind of universal. Often this theta 1 in the first picture where the ray of light is incident from medium 1 to medium 2, that theta 1 would often be called the angle of incidence. Okay, that's the angle of incidence. And the other one, the theta 2 in this particular situation, is the angle of refraction. Okay, but rays of light are perfectly reversible. So these are interchangeable. So I can change theta 1 to theta 2 and theta 2 to theta 1. Or if a ray of light is incident at an angle theta 2, so if the angle of incidence is theta 2, then the angle of refraction for the same set of media n1 and n2 would again be theta 1, right? So that's sort of the idea.